Globally, we have a serious problem when it comes to teeth. Record numbers of children are having extractions for decayed teeth, and almost all adults have some degree of tooth damage. Historically, dentists have treated the problem by drilling the tooth and plugging the hole with a filling compound. It works, but it can be unsightly, fillings can loosen and need replacing, and your teeth are ultimately made weaker for it. Now there might be a new option on the horizon, because researchers at Queen Mary University of London have developed a way to regrow tooth enamel, the tough white stuff on the outside of teeth. They found the right pair of proteins which, when put together, can pull the chemical building blocks of enamel out of saliva and lay down crystals like a new road surface over a damaged tooth surface. I heard how it works from lead author Alvaro Mata.
We make materials using molecules, and the molecules that we use are proteins. This is actually the way that nature makes things. Our bodies are made by putting proteins together. Imagine our human bodies being a structure of Legos, where each Lego piece, it's a protein or a group of proteins or different proteins that come together in a specific way. And we are able to use these proteins and begin to build with them as if we were building a Lego structure. In this case, we put together these proteins that have a specific properties, and when they come together, they trigger the formation of apatite. So when you expose them to calcium and phosphate ions, they form apatite, and they begin to direct the growth of the nanocrystals that also acquire a hierarchical organization, just like for enamel.
What proteins are you starting off with?
Elastin, which is a protein found in very strong and elastic tissues in our body, like tendon and ligament, and also the protein staphyrin. Staphyrin is found in saliva. It is known to bind calcium phosphate, is known to actually take care of the enamel in our teeth. So we're producing a protein that looks like elastin and it looks like staphyrin. The protein in the material that we make, that is not the actual enamel-like material. The enamel-like material is when it actually grows on it. And that's the calcium phosphate that is actually found in saliva. So when we tested this, we used an environment and a solution that looks like saliva. It had the same ions and composition, and we saw that in those conditions, the crystals were able to grow in this highly organized and hierarchical manner within our matrix.
So is the idea then that you'd paint this on, and because of the conditions in the mouth, this would stimulate regeneration?
Correct. That's our ultimate aim, not only to repair it, but actually to regenerate it. So most of our tissues are able to regenerate. This is how these tissues actually last a lifetime. In the case of enamel, this is a tissue that is formed during development, and then it does not change. So actually regenerating a tissue that does not have the capacity to keep remodeling has been very difficult, and it has not been done. So if we are able to create these similar crystals organized in a similar fashion, which means high stiffness, high resistance to different environments, and high stability, then we should have a material that, just like enamel, is able to perform and be stable for a long time.
For someone who's suffering from dental problems, what difference could this make?
What we're aiming for is to create a kind of patch that can be laid on top of a tooth, either an area where enamel it's been lost or is diseased, regenerated. We should be able to really recreate the tissue, to remove that problem, remove the sensitivity, the pain that the patient may have, in a way that it is the body regenerating itself, using the ions present in the body to recreate these crystal structures.
That was Alvaro Mata, and that study was published in Nature Communications.